All right, today we have question number 6 from the 2019 AP Calculus BC free response section. This is a no calculator problem. We're given a graph and a table with different derivative values for this function f at x equals 0, and it tells us that a function f has derivatives of all orders for all real numbers x. A portion of the graph is shown above, along with the line tangent to the graph of f at x equals 0. Selected derivatives are also given above, and asks us to write the third degree Taylor polynomial for f about x equals 0. So first we can try to imagine the general term for the general Taylor polynomial for a function about x equals 0. And that's going to be that p of x is going to be equal to f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 times x squared, and so on and so forth. But we're only looking for the third degree term, so we're only going to go to this third degree. F triple prime of 0 over 3 factorial, which is 6 times x cubed. And we're given all the information that we need within this problem. We can see that f of 0 is just going to be 3. It's the line of this curve where it intersects the y-axis. And we can see that f prime of 0 is going to be the slope of the line tangent to f at x equals 0, which, using some simple math, we can see it goes down 2 and over 1 for a slope of negative 2. And then we're given the other derivative values for different n values at x equals 0. So we can plug all those in to get our third degree Taylor polynomial. And we find that the third degree Taylor polynomial is going to be equal to 3 minus 2x plus 3 over 2x squared minus 23 over 12x cubed. Part B now asks us to write the first 3 non-zero terms of the Maclaurin series for e to the x, and then to write the second degree Taylor polynomial for e to the x times f of x about x equals 0. So the first thing we're going to want to do is write out the Taylor series for e to the x, which is going to be equal to 1 plus x squared over 2 factorial, or simply 2. Now, in order to find the second degree Taylor polynomial for e to the x times f of x, we're going to need to multiply the two Taylor polynomials for each function together. So e to the x times f of x is going to be equal to the product of both of their Taylor polynomials. Now, you'll notice that I only used the first 3 terms of the Taylor polynomial for f of x, and that's because it asks us to find the second degree Taylor polynomial for the e to the x f of x function, and so it's unnecessary to include that fourth term, which is cubed, with the x, because that will give us a third degree at its minimum. Now, doing some simple distribution algebra, we can now combine these terms that we have here, and we get that e to the x times f of x is equal to 3 plus x squared. And that is only to the second degree Taylor polynomial. Now we're going to define some function h such that h of x is equal to the integral from 0 to x of f of t dt. And we're going to use the Taylor polynomial we found in part A to find an approximation for h of 1. So the first thing we'll do is copy the Taylor polynomial from part A for our convenience. And you'll recall that this Taylor polynomial was an approximation for f of x. So now we're looking for h of 1, and we'll say that h of 1 is going to be equal to the integral from 0 to 1 of f of t dt. Now, because we have the approximation for what f of t is equal to, we're also going to say that it's equal to the integral from 0 to 1 of this Taylor polynomial function. 3 minus 2x plus 3 over 2x squared minus 23 over 12x cubed dx. Now we're going to find the antiderivative and use the fundamental theorem to find out what h of 1 is equal to. And now, computing this, we find that h of 1 is equal to 97 over 48. I skipped some of the basic algebra, but you have to combine a number of fractions. And I made a mistake, and this is actually an approximation, so we should say that h of 1 is approximately equal to 97 over 48. The final part of this problem asks us to show that the error bound for this for the Maclaurin series for h is going to be less than or equal to 0.45. It essentially also tells us that h of x is an alternating convergent series, which means that we can apply the alternating series error bound in order to find the maximum error. And we know that the error for the Maclaurin series for h of x is going to be less than the magnitude of the next term. Now you'll recall from part B that we defined h of x as being approximately equal to this integral using the Taylor polynomial of the third degree for f of x. Well, now in order to find the error, we're going to need the next term. And in order to find the next term, we need to find the fourth degree term for f of x. So we'll go back up to our front to find out what that fourth degree term is. And we'll remember generally that the fourth degree term is going to be f to the fourth of 0 over 4 factorial times x to the fourth. And we see from our chart that f to the fourth of 0 is equal to 54. So now we can say that the fourth degree term for the f of x Taylor polynomial is going to be 54 over 24 times x to the fourth. Well, if we want the next term for h of x, we're going to need to take the integral of that. So the next term for h of x is going to be equal to the integral of 54 over 24 x to the fourth dx. And now if we're going to try and find the error, that's going to be that integral evaluated from 0 to 1. And now since we're using that integral to find the error, we can also take the magnitude of that integral. So calculating out the antiderivative, we find this integral is equal to 54 over 120 times x to the fifth, evaluated from 0 to 1, which when we plug in those numbers, we get is just equal to 0.45. So as we recall, the start of this question asks us to find that the error differs from the actual value of h of 1 by at most 0.45. So we know that the error, which is less than 0.45 because of our now test, and 0.45 is less than or equal to 0.45.